Welcome back to part 2 of forecasting, in which we will take the averaging techniques. The first averaging technique is the simple moving averages. First of all, let's look at different possible approaches to this concept of averaging. Here is the data. Again, let me try to explain what the example is, as we did in the case of forecasting error. For house number 1, our forecast was 250. It turned out to be, actually, the actual duration turned out to be 260. Based on this, we found out to be 260. It turned out to be 245, and so on and so forth. We have completed 10 houses, and now we are to forecast house number 11. I would like to make one point here, which is extremely important, that whatever averaging technique you may use, it is the actual data and not the forecasting data which matters. The past forecasting data becomes irrelevant once we have the actual data of the past events. Of course, there is one exception in the form of exponential moving averages, in which case we take both the past forecasting as well as actual data. Other than that, it is always the actual data which is used for forecasting. Okay, the problem is to work out the forecast for house number 11 using averaging techniques, and the first one is the simple moving averages. Let us first of all plot the data. These are the same values, actual values, 260, 245, 255, 255, etc., as depicted in the actual duration column. And we have to find out the forecast for house number 11. One approach could be to take the mean of the entire past data. And if we do that, we get a figure of 250, and we can draw a line here indicating 250. And based on which we can say house number 11 is likely to take 250 days to complete. Another approach could be to skip the past data, particularly the first data point. Why? You could argue that if you are a builder, that was your first house, you were not very experienced. There were a lot of teething problems, which over a period of time you have overcome. Therefore, for you, this point may be an outlier. Therefore, it should not be considered into calculation, in which case you might like to take average of all the 10 houses except number 1. In this case, your answer would be 248.9. Another approach could be to discard the previous past data, distant past data altogether, and take the recent data. How recent? 3, 4, 5, 2, how much? So the depth to which you want to go into the past is referred to as the K value. K is equal to 3 means you are interested in averaging the data of the last 3 events only. K is equal to 4 would imply averaging the data of the last 4 events only. So if you take K is equal to 3, that means you're going to take these 3 values, previous, the one before that, and the one before that, last 3. And this averaging gives you a value of 248. If you want to take K is equal to 4, that means averaging the last 4 data points, it becomes 249.3. And if you take k is equal to 5, these 5 data points, 248. So it is entirely up to you what value of k to take, although we are going to discuss this in a while as to what would be the most appropriate value of k. But as professional project managers, the value of k is at your discretion, and in fact, you will not use your discretion, but you will use your experience and hardcore statistical calculations to find out what value of k to take. Before I proceed further, let me make one very important point. If you look at these figures, you will find that the average value always lies between the maxima and the minima of the data set. If when k was equal to 3, that means these three, the minimum value was 242 and the maximum was 254. And as you can see, the value lies between the maxima and minimum. It cannot be less than minima. It cannot be more than the maxima. And this is a sure check in any calculations involving forecasting. So K value dictates to what depth do you want to go into the past. And let me throw in a brain teaser here. Pause the video and I'll try to answer this question. What will be the forecast known as if K is equal to 1? Of course, if K is equal to 1, that means you are taking the previous actual value only. And previous actual value is nothing but the naive forecast. So when K is equal to 1, this is just like saying it is the naive forecast. Let's do a little graph work with simple moving averages. To be able to understand why simple moving averages are called moving. Here is the same data. Sorry, I just got it wrong. Yeah. Let's try to build up this concept. Where does moving come in? Or how does moving come in? Let's say our first house, the project has started and we are going to build our first house. Our forecast was 250 by any method, PERT, analogous, parametric, whatever. And the actual value turned out to be 260. Based on these two, the forecast for the next house was 262, and it actually turned out to be 245. Based on these two, the forecast for the next house was 250, and it turned out to be 255. We assume that the value of K is equal to 3. If value of K is equal to 3, that means you require a minimum of 3 actual values, 3 past actual values. And now we have achieved those 3 actual values. So we can use these 3 values to forecast the duration of house number 4. So what is the average of these 4? This is 253.3. If the actual duration of house number 4 comes out to be 246, we can now forecast for house number 5 by picking up the latest value, latest data point, and discarding the oldest. Picking up the latest and discarding the oldest, Why? Because we have to keep k is equal to 3. We have to take the average of 3. That is where the movement lies. That means picking up the next and discarding the tail. Here it goes. We have picked up the next one, discarded the earliest, and the average is 248.7 for house number 5. Again, if the actual A for house number 5 is 254, now we have got the latest data. We can pick up the latest data and discard the earliest data. So that is where the movement lies. And we can continue doing this. And let's say we have completed house number 10. For house number 11, we'll take this data set to find the forecast for house number 11. Now I'm going to show you the same thing in animation and the concept of moving. Someone asks you why simple moving averages are called simple moving averages, or where does the concept of moving come from? So that will now become abundantly clear once you see this animation. So here is the same data set, 260, 245, 255. We got 3 actual values. So now we are in a position to find out the forecast for house number 4, because k is equal to 3. So we got the 3 data points. So we can find out for 4. And once we have done that, sequentially, we will continue picking up the latest and discarding the earliest. Here we go. So that is why simple moving averages are called moving averages. This was data set for k is equal to 3. And if k is equal to 4, we will get these figures. We can now make a graph. We can convert this into a graphical data, this one here or this one here, same thing. If we draw the graph, this is what we get. First value 260, 245, 255. 260, 245, 255. I'm going to transfer this graph as well as this data, this graph as well as this data onto the next slide. It is the same graph and the same data. Because of space constraints, this was supposed to be on top. I've just taken it to one side just to conserve some space. And what I'm going to do next is blow up this chart. In fact, I'm going to exaggerate it, pull it or stretch it vertically. And this is what this graph will look like. It is the same graph, 260, 260, 245, 245, 255, 255. So these are the actual values. Let us now plot the forecasting graph, first at k is equal to 3. At house number 4, the forecast value was 253.3. House number 5, this. So when we plot k is equal to 3, this is what we get. What do you notice? The first thing you notice is the smoothing. The data has smoothed. The variation has reduced. And based on k is equal to 3, we get forecast for house number 246, house number 11 to be 246. Let us now plot this data, which is for k is equal to 4. For house number 5, instead of 248.7, we now have 251.1. So let's plot this green data, which is for k is equal to 4. And this gives us a forecast of 247.8 as reflected over here. Now, some very interesting conclusions can be drawn looking at this graph. First of all, if you compare green k is equal to 4 with this red or brown, which is k is equal to 3, you find there is more smoothing with k is equal to 4. So the conclusion to draw is that as you increase the value of k, smoothing increases. Then again, if you make a comparison between green and red, you can see that there is less variation in green, or the data becomes less representative of the change, or the data becomes sluggish. So higher the value of k, more sluggish or less representative data become, less representative of the change. If you make k is equal to 5, this will almost become a straight line, which will indicate that perhaps the data is all going in a straight line, which is definitely not the case. The data is gracefully zigzagging along a certain mean. So the second conclusion is, with increased value of k, the sluggishness increases, or the data becomes less responsive to change. And the third point is, if you compare these forecast values with the previous actual value, actual, not the forecast, previous actual value, you find that higher the value of k, farther is the forecast from the previous actual. Let me repeat. Higher the value of k, farther is the forecast from the previous actual. You can take any other example in the past. Forecast for house number 8. This is the forecast for house number 8 at k is equal to 4. And this is the forecast for house number 8 at k is equal to 3. K is equal to 4 is farther from the previous actual value. The previous actual value was 253. K is equal to 4 gives you a forecast which is farther from the previous actual value. Or smaller value of k gives you a forecast which is closer to the previous actual value. Here k is equal to 3 is closer to 253 than k is equal to 4. Here k is equal to 3 is closer to the previous actual forecast than 247 or k is equal to 4 is. So these three conclusions are summarized over here. K value, when it comes to smoothing, K value acts like a rheostat on your iron. Just like if you have cotton or linen clothing with lot of wrinkles, then you will set the rheostat to a very high heat setting so as to iron out the variations or the wrinkles. But if it is nylon-based fabric, then of course the wrinkles are few and you will keep the thermostat to a very low value. So consider K value to be very similar to the rheostat of your iron. The next point is, as project managers, what value of K you should consider? The answer is very simple. Whichever value of K gives you minimum error. I have found a very good example from the net, which I would like to share with you. It is this example over here. If you see these black dots, these represent actual data. And the blue line represents the forecast. We are going to look at this forecast, or the blue line, how it changes with the changing value of K. We'll start with K is equal to 1, which, as I said earlier, is the same thing as naive forecast, also referred to as the random walk. If you look closely over here, because k is equal to 1, that means you are taking the previous actual value. And you are taking the previous actual value. You can see the blue dot is at the same level as the black dot. These red lines are the 95% limits. 95% in statistics is the statistical significance value. It is normally taken as 95%. What this statistical significance represent is the quality of your data, or the degree of confidence you have in the data, or the degree of assurance you have in the data that this data is not by random chance, it is actual data. It is not a fluke. So that is 95% assurance or 95% statistical significance value, and you do most of your research work based on 95% statistical significance figure. Anyway, that was an aside. What is important is this thing here, that k is equal to 1. This is the figure. When k is increased to 5, see how the data has smoothened from the previous one. This was the previous one. See the variations, and now see the variations as k has increased. Variations have reduced. Data has become smoother. This is k is equal to 9. Data has become even more smooth. And this is k is equal to 19. It is almost becoming cyclic now. Those rapid variations have gone. So which value of k will you take? 19 as here, 9 over here, 5 as in here, 1 as in here. So all these k values are there. Which value to take will depend upon the error. So using these 4 or 5 charts models, you can work out different errors. And these errors are tabulated over here. This column indicates root mean square error. This column indicates mean absolute error. This is mean error. This is unreliable anyway, so let's take it out. And as I said, we haven't gone into mean absolute percentage error and mean percentage error, so let's not bother about. Let's concentrate on these two. If you are working in root mean squares, or your company policy, which is given in OPAs, is to work in terms of root mean square error, then if you look at this column, the minimum value of root mean square error is here, which is k is equal to 5. So you will choose k is equal to 5. But if you are working in terms of mean absolute errors, or your company policy as given in OPAs is mean absolute error, then the minimum error in this column is this one here, which is k is equal to 9. So you will use either k is equal to 5 if you are using root mean square error, or k is equal to 9 if you are using the mean absolute error. So this is the dictating factor for the value of k. I repeat one last time that whatever value of k yields the minimum error which you use, that is the value of k to be selected. That was simple moving averages. Now let's take a version of simple moving averages called the weighted moving averages. In simple moving averages, when we let's go back. In simple moving averages, let's take this data set. This is the actual. These are the actual values. I haven't written the previous forecast values. These are the previous actual values. So if you are to work out the forecast for house number 11 using simple moving averages, you will take the simple mean of these three. By simple mean, it means you are giving equal weightage to all these figures. The total weightage is 1 or 100%. So that means the weightage of each one of these is 33.3333. The sum of weights being 100. However, you may decide that within this k is equal to 3, you are going to give more weightage to the latest and least weightage to the earliest. In this example, you decide that, okay, I'm going to give 50% weightage to the latest, 30% to the one before that, and 20% to the one before that, the earliest. When you do that, all you have to do is multiply this by 20%, this by 30%, this by 50%, making sure that the sum of the weights remain 100%, no less, no more, exactly 100%. So this averaging, in which you vary the weights to each of the previous data points, is referred to as the weighted moving average. So in this case, the simple moving average is 248, but the weighted moving average, in which case this is 50%, this is 30%, this is 20%, we get 248.6. So this is the concept behind weighted moving averages. Again, please note, whether it is simple moving averages, whether it is weighted moving averages, or whether it is any other average which is going to come, the forecast figure has to lie between the maxima and the minima. In this data set, the minima is 242, the maxima is 254, and you can see it is lying in between the two, the two extremities. No less than minima and no more than the maxima, something in between. So that was weighted moving averages, and now we can transition to the centered moving averages. Centered moving averages. These are used when we have to work out seasonal indices. What is meant by that? If you are owning a boutique and you deal in all sorts of clothing, winter as well as summer, and you place an order for your clothing onto some clothing factory. Let's take t-shirts. Are you going to place an equal or uniform order for all the 12 months of the year? Definitely not. You will place a reduced order for winters and a huge order for summers. How do you decide that? Well, one tool that is available to you is referred to as the seasonal index. And this concept of simple moving averages helps you find out the seasonal indices. Let me give you an example and it will become clear. It is again the same data. These are the actual durations. In order to work out the centered moving average or the seasonal index, and let's start with k is equal to 3, which is odd because it is slightly different when the k becomes even. As per simple moving averages, we take the mean of the 3. But instead of placing or considering this to be the forecast for the next event, which is 4, this mean value is placed at the statistical middle of the data set. The statistical middle of this data set is house number 2. So the mean of this will not be placed here, but placed against number 2. Then the next one is picked up and the earliest one is dropped. And because this is the data set 2, 3, 4, for which the statistical middle is 3, the mean is placed in front of 3. And we continue doing this exercise till we reach the end. And if we have done this exercise correctly, the number of blank spaces at the top and below will be the same, 1 in this case. Of course, if it is 5, it will be more in this case, 2 if it was 5. So once these averages have been found, the next stage is to find the index. Index is nothing but dividing the actual by the average. So in case there is no value over here, so there's no point dividing. Over here, the actual duration was 245. The estimate for the next was 253.3. So this divided by 3 gives us an index of 0.97. This divided by this gives an index of 1.03. And we continue doing this. These are the individual indexes. We can take their mean. This is roughly equal to 8. So 8 divided by 8 is 1. At the moment, this example may not have been making much sense to you, but once I give you an actual example, it will become very clear. What happens if k is equal to 4? If k is even, like k is equal to 4. Well, we again take k is equal to 4, so we take these 4 data points, but the point is where to place the data. In front of 2? No, because that is not the statistical middle. Against house number 3? No, because that is again not the statistical middle. What is the statistical middle? Well, for the time being, we assume we can break up houses into pieces. So house number 2.5, this line over here, which represents house number 2.5, is the statistical middle. And that is where we place the data, 2.5. For the next centered moving average, we pick up the latest and discard the earliest. And this time, the statistical middle of 2, 3, 4, and 5 is 3.5, and that is where we'll put the data. And we will continue doing this. Now we have to find out the index by dividing this by this. But which one to divide? We divide 255 with what? With this or this? Well, obviously, it has to be 1. So if k is even, we have this little problem, which is solved by doing a centered moving average a second time. So we've got these figures. What we can do now is apply centered moving averages onto them with k is equal to 2. That means we only take 2 data points. So we average these 2. When we average these 2, the statistical middle of 2.5 and 3.5 is 3. So we can place this averaging data now in front of 3, and we can carry on with our business. Here we are. So when we average these 2, we get this figure. And as you can see, the statistical middle of 2.5 and 3.5 is 3. So now we are in a position to divide 255 by 250.8, to get our index. We can continue and work out the rest. Now we can find out the indices. Again, take the mean, which comes to 0.99. Okay, just keep this concept, this technicality in mind, and let's do an interesting example. There is a restaurant and its manager, having done MSPM or having done this centered moving averages, wants to apply centered moving averages into planning his logistics. Take any item in a restaurant, milk. The restaurant owner has to place an order for milk to some dairy, to dairy farm, or to some vendor, milk seller. How much milk should he order for Sunday or Monday or Tuesday or Wednesday? And likewise, other commodities. And he can apply the same principle for human resources. How many waiters he should hire or he should have on a Sunday or Saturday, and how many on a Wednesday. So what he can do is collect the data over a period of time. He collects the data over, let us say, 3 weeks, and these are the figures he gets. In the first week, the restaurant served 55 customers, 67, so on and so forth. This is the data for second week, and this is the data for the third week. This is good data, and this is sufficient data. What can be done is that this data can be placed in in 2 columns, the entire data, days and customers. Sequentially, first week, second week, third week, which is done in this chart over here. So this is week 1, this is week 2, this is week 3, and these are the customers. The restaurant manager can now work out the centered moving averages, but what value of K to take? Well, there are 7 days in a week. We are talking about days, and there are 7 days in a week. So logically, K should be 7. So if K is equal to 7, that means that this data has to be averaged. And where is the average to be placed? At the statistical middle of the week. So starting from Monday, 1, 2, 3, 4, 5, 6, 7. Alhamdulillah. Thursday is the statistical middle. So the mean of this 7-day data is placed in front of Thursday. Then the data for Monday will be picked up and the previous Monday will be discarded. And the average would be placed in front of Friday. And this exercise will be continued till we have achieved averaging of the last 7 days. If this has been done correctly, the number of blank spaces at the top, which is 3, is the same as the number of blank spaces at the bottom. The next stage is index. So we have to divide this with this to get the index. Of course, this data is irrelevant now because this doesn't have a CMA. Here we are, these are the indexes. The point is, we have now, for Thursday, we have 3 indexes, 1, 2, and 3. And for the rest, we have 3. Therefore, we have 2. So for Thursday, we have 3. For the rest, we have 2. That means we can find the mean average for each day. For Monday, it comes to 0.64. For Thursday, 1.05. 7, for Monday 1.255. Now these indices say a lot about logistics. If one represents 100 liters of milk, which the restaurant manager has to order, then on Saturday, he would be placing an order, multiply this by 100 liters, he will get a figure of 125.5. That means he'll place an order for 126 liters for Saturday. For Monday, multiplying this figure by 100, he has to place an order for 64 liters. If one represents 100 kg of chicken meat, then on Sunday, multiply this by 100, he will be ordering 116 kg of chicken meat. And on Tuesday, he will be ordering this multiplied by 177.5 kg of chicken meat. And he can apply this index for any other commodity, even for HR. If one represents 10 waiters, then on Monday, he needs, multiply this by 10, he needs only 6.4 waiters, that means 6 or 7 waiters. But on Thursday, he requires 12.55 waiters. That means 12.3. Again, if you now recall the concept of resource smoothing, obviously he has minimum requirement on a Monday. So he could perhaps keep 6 waiters on his permanent staff. And for the rest of the days, since he has 6 on Monday, for Saturday, he's going to hire an extra 6 or 7. So this is the beauty about centered moving averages, that they give you indices which you can then use to find out your logistical requirements for any particular day, or for any particular house, or for any particular event. Well, this was k is equal to 7, 7 days in a week. 7 is an odd number. What if k is even? We assume that after doing brisk business over the weekend, the restaurant closes on Monday. So there is no business on Monday. Therefore, this restaurant is now open for 6 days a week. And we take the same data again, except the Monday is missing. K is equal to 6. So we take 6 data points, find where the statistical middle is. The statistical middle is over here, which is Thursday and a half, or Thursday 0.5. So we take the mean and put it against Thursday and a half. And likewise, we do this exercise for all. And if we have done it correctly, the number of blank spaces on top is 2.5, and the number of blank spaces at the bottom is 2.5. Because k is even, we have to do this exercise twice. We have to find centered moving averages a second time by taking k is equal to 2. So we average them again by taking k is equal to 2. So average of these two. Now this line was Thursday and a half. And if now you average these two, this data will lie in front of this line. And where does this line point to? This line points to Friday. So averaging these two data points at k is equal to 2, we get 83.02. And if you now, it is this is the statistical middle. And if you now extend the statistical middle in the other direction, it is Friday. So for Friday, this was the customer, this was the forecast. We can divide, this is the actual value, this is the forecast. We can divide and get the value of index. So first of all, we can find out CMA for for the entire data set. And having found that, we can now divide 90 by 83.06, 98.82. We'll get these indices. Again, we can take the average for each day, and these are your new indices based on 6 days a week. So that, ladies and gentlemen, was the concept of centered moving averages. And now we are left with one, which is called the exponential moving averages. Exponential, as you know, the word exponential means having a power. Like 2 raised to the power 3. 3 is an exponent. Or this is an exponential figure, 2 raised to the power 3. I said earlier that whenever using a forecasting method, we always take the previous actual values, with one exception, and that exception has come. That is the exponential moving averages. In exponential moving averages, we consider not only the past actual data, but also the past forecasted data. The equation is very simple. This is the forecast for the next event. So if 10 events have taken place, this is the forecast for 11. N plus 1, 10 plus 1, 11. What does it say? The forecast for the 11th event is equal to the previous actual, Y stands for actual, and the previous forecast. That is for starters. So we take the previous actual and the previous forecast. However, if we give a weightage of alpha to the previous actual, then we give the complementary weightage to the previous forecast. What does that mean? It means that if we, for example, give a weightage of 70% to the previous actual, then its complementary is 30%, and that is the weightage that is given to the previous forecast. It is as simple as that. Alpha could be anything. It shouldn't be 0, it shouldn't be 1, it should be something in between. It shouldn't be 0%, it shouldn't be 100%, it should be something in between. I would like to explain the concept of exponential. Why exponential moving averages are called exponential? Going back to the previous slide, this is the equation. There is no indication of any exponent. Is there any raised to the power? The power of everything is 1. So where is the element of exponential? One would have liked to see raised to the power 1, raised to the power 2, raised to the power 3, 4, 5. But there is no indication of that in this formula. So where is the exponential bit? Well, this will be best understood by these dolls. These are Russian dolls. These are nested dolls. When you purchase this doll, you purchased this doll. When you open this doll, you get this doll. You find this doll. When you open this doll, you find this, and so on and so forth. Or in other words, this doll goes into this doll, then this doll goes into this, into this, into this, into this, into this. We have something very similar in Pakistan also, we have nested tables. Those TIPI tables, set of 3 or 4. There's one big table, and you can pull out 3 tables from the big table, then 2 tables from the next, etc. Or you can insert the smallest table into the next bigger, and then those 2 tables into the next bigger, and then those 3 tables in the biggest table. So keep these Russian dolls in mind when understanding the element of exponential in exponential moving averages. What I'm going to do is build up this concept for you step by step. It has no examination value, but it has a lot of conceptual value. I'm going to write here forecast value and the actual value. And then whatever is the actual value, what weightage is given to the previous actual value, I will write over here. Let us start the exercise. For instance, you are making the first house, and that is your forecast. House number 1 forecast is F1. When the house has been built, it has actually been built in Y1 days. So this is for house number 1. 1 indicates house number 1. So you have got the previous forecast, or the forecast for house number 1 and the forecast for house number 2. What is going to be the forecast for house number 2 now? Going by the exponential moving averages formula, if we have 70% weightage, or value of alpha is 70%, then the forecast for house number 2 is 70% of this value and 30% of this value. So F2 is 70% of this value and 30% of this value. That is F2. So what is the weightage given to Y1? 70% or 0.7. This I'm going to write here, 0.7. And I'm going to multiply it with one factor, which is 0.3. What is 0.3? It is complementary of 0.7. So if it is 0.7, it is 0.3. If it is 0.8, it will be 0.2. If it is 0.9, it will be 0.1. And raised to the power 0, anything raised to the power 0 is 1. Therefore, it makes no difference. It stays as 0.7. 1 multiplied by 0.7. Okay. So this, the forecast for house number 2 was F2. This house has been completed in Y2 days. So this is now the actual value of house number 2. We have the forecast and the actual values of house number 2, based on which we can forecast house number 3. Again, what is the value, forecast value of house number 3? 70% of this and 30% of this, which means this. 70% of this and 30% of this. But hang on, what is this? This is this. And what is this equal to? This is equal to this. So if we now substitute this F2 with this value, we get this figure. And now if we rearrange, we get this figure. 0.7 Y2, 0.3 multiplied by 0.7 Y1, and this is the weightage to the forecast. Now, if we transfer these weightages to the same table, the weightage given to Y2 is 0.7. Again, it is 0.7, so we will write it like this. And what is the weightage given to Y1 now? 0.3 multiplied by 0.7. So here we are. What has happened? Look, the weightage given to Y1 has now reduced from 70% to 21%, or from 0.7 to 0.21. And the weightage of Y2 is, of course, 70%. And if we write it in the same format, what do you see here? It is 0.3 raised to the power 0, but 0.3 raised to the power 1 now. That is how it is going as written over here. You see here 0.3 multiplied by 0.7. So from 0.3 raised to the power 0 has become 0.3 raised to the power 1. I hope you see now the element of exponential or exponents coming up, raised to the power something. And it will become even more clear shortly. We now assume that house number 3, this was the forecast, was actually completed in Y3 days. We have now the data for house number 3, both actual data and forecast. Based on this, we can find out the forecast for house number 4. What will be the forecast for house number 4? 70% of this, 30% of this. So F4 is 70% this and 30% this. But what is F3? We just found out that F3 is equal to this. If now we substitute F3 with this value, this is what we get, and when we rearrange, this is the sort of expression we get. See the weightage given to the past values. Y1, the weightage is 0.7. Y2, which is this Y3 is the latest, 70% weightage. The weightage given to Y2 is 0.3 multiplied by 0.07. And weightage given to Y1, the earliest, is 0.3 raised to the power 2. So now we can transfer these. This is for Y3, so this goes here. This is for Y2, it goes here. This is for Y3, Y1, the earliest, this goes here. And look what is happening. First of all, as you go in the past, the weightage given is reducing 70%. For Y2, the weightage is 21%, and for Y1, the weightage has gone reduced to 6.3%. But where is exponential? You see here, 0.3 raised to the power 0, 0.3 raised to the power 1, 0.3 raised to the power 2. This is precisely what is happening here. This was the smallest doll. Then it entered into the next doll. It became a part of Y2. Then these two dolls became a part of this lady over here. Exactly, this doll becoming a part of this doll. Then these two dolls becoming a part of this doll. Then these three dolls becoming a part of this doll. Likewise, this little doll becoming a part of this bigger doll. Then these two dolls becoming a part of this lady over here. And in the process, you can see the exponents. 0.3 raised to the power 0, 0.3 raised to the power 1, sorry, 0.3 raised to the power 2, 0.3 raised to the power 1, 0.3 raised to the power 0. We assume that the actual value of house number 4 was Y4. We have got data for house number 4, actual forecast. We can find out the forecast for house number 5 by taking 70% of this, 30% of this, and I don't want to clutter this slide with more expression. I think you can now extend it, and you will find that these three dolls have merged into the fourth doll. And see the weightage. Now the weightage given to Y4 is 70%. The weightage given to Y3 is 21%. 21%. Weightage given to Y2 is 6.3%. And the weightage given to Y1 has reduced. Now see this one here. As you progress into the future, the weightage given to the previous forecast reduces exponentially. 70%, 21%, 6.3%, 1.89%. And it is shown exponentially over here. 0.3 raised to the power 0, 0.3 raised to the power 1, 0.3 raised to the power 2, 0.3 raised to the power 3. By the way, I hope you know okay, when it is a decimal, when the number is less than 1, and as you increase the power, the value reduces. 0.3 raised to the power 0 is 1, but 0.3 raised to the power 1 is 0.3. 0.3 raised to the power 2 is 0.09. So the value is reducing if the value, if the number is less than 1. So if you are asked why exponential moving averages are called exponential moving averages, the answer is the weightage given to the past data reduces exponentially, as seen over here, from 70% to 21% to 6.3% to this. And exponentially, you can say 0.3 raised to the power 0, 1, 2, 3. And likewise, you can see here, the weightage given to this is also reducing exponentially, 70%, 21%, and so on and so forth. So we can generalize this equation over here, which you need not see, but I hope the point becomes very clear as to why exponential moving averages are called exponential moving averages. Okay, the last thing is to give graphical treatment to this equation. Let's take a slightly different example. I said I would be taking the same example, but I thought maybe a different example would be in order for this particular case. This is the data. This was the forecast and the actual, and then the forecast data was calculated using this this formula over here. So this is the data, this is the actual data, this is the forecast data, and now we have to depict it. By the way, we have taken alpha equal to 30% or 0.3. If we have to plot it, this is the forecasting data, this is the time series T1, T2, T3. This is the data. Excuse me. And this is your actual data, 71, 70, 69, 71, 70, 69. And let us plot this, the red data, and this is as indicated, and we get forecast for house number or for event number T13, time 13, we get 72.6 as indicated over here. What do you notice? That like K value, alpha value also smoothens. See, the variation in data has drastically reduced with when alpha is applied. The point is, does alpha behave in the same way as K does? That means, does smoothing increase with increasing value of alpha? Well, for that, we have to uh, take different values of alpha and see uh, what happens. This is the same data, actual values. And over here, what you're going to see is a lot of data. Don't be scared. This is for values of alpha ranging from 100% to 0%. Although I had said that it is never 100 and 0, but for the sake of argument, let us take it from 100 to 0, or from 1 to 0, and in decrements of 10%. So 100%, 90%, 80%, so on and so forth. If the value of alpha is 100%, that means 100% weightage is being given to the previous actual and 0% to the forecast. Again, this is nothing but the naive method, which is very evident over here. What was the previous actual? 71. So what is the forecast? 71. What was the previous actual? 70. So what is the next forecast? 70. 69, 69. So this is nothing but the naive method again. But when we take alpha to be anything other than 1, we get these figures. When alpha is 0, that means we are giving the entire weightage to the previous forecast. We are not considering the previous actual, which is unrealistic, but for the sake of argument, I've just added it over there. So these are the values at alpha is equal to 100%, 90%, 80%, 70%, 60%, 50%, etc., etc. Obviously, this tabulated data means nothing, so let us plot it. First of all, let's plot the actual values and then the values at different values of alpha. So these are the actual values. I'm going to now click, and animated charts will come up, starting with alpha is equal to 100%, then 90%, 80%, 70%, 60% as per this legend over here. It will start with 100%, then 90%, then 80, then 70, then 60, 50, 40, 30, 20, 1, and 0. So as they come up, I will speak also. So just see what happens. What is going to happen is that alpha value is decreasing from 100% to 0%. So this is the variation. Is the variation going to increase or decrease with increasing value of alpha? This is what is to be seen. So let us starting with alpha is equal to 100%. 100, 90, 80, 70, 60, 50, 40, 30, 20, 10, 0. Let me play it again. The value of alpha is decreasing from 100 to 0, 90, 80, 70, 60. And see what is happening to this graph. Is it flattening, or is it or the variation going to increase? We go again. 100, 90, 80, 70, 60, 50, 40, 30, 20, 10, 0. I think you can make out that if the value of alpha increases or if the value of alpha reduces, smoothing increases, which is direct opposite to K value. In K value, smoothing increases with increased value of K. It is opposite over here. And we can draw this conclusion, a very important conclusion over here, that is large value of alpha, 90%, 80, 70, 60, less smoothing of the data, small value of alpha, say 10, 20, 30%, etc., more smoothing of the data. With that, ladies and gentlemen, we come to the end of this part.